This recording is protected by copyright. No part may be reproduced without the prior permission of the University of South Australia.
All right, let's get cracking, shall we? I'm not going to talk about this now. I'll talk about it close to the end of the lecture after we've finished going through the notes. If you have a question already. You know what? I didn't even bring the next page because I'm always worried I'll press the wrong button and it will show you all the questions. Actually, the next page is blank, I think. The page after's got the questions. 1, 2, 3. Yeah, I think the next one's blank. Okay. Anyway, I'm going to talk about this at the end after we've gone through the notes. I haven't got much housekeeping today except that don't forget it's quiz 6 this week. Something's wrong with it at the moment, but as soon as I get back to my office, I'll try and get it reopened up. I have somebody's USB stick that was found in the lecture theatre on last Wednesday. It's possible it was from here. It's possible it's from the lecture before us. If it's yours, come grab it. I've already looked. There's nothing exciting or helpful on there. I know, I was a bit brave. Okay, does anybody have any other housekeeping questions? No? Yes, Michael. I should be able to get everything out before the exam, for sure. I'm hoping to get the pracs and assignment 3 out, hopefully this week. Assignment 4, hopefully next week. But I should be able to get it all out before the exam. I can't see any problems with that at the moment. No, it's on there. Yeah, no, it's attached to this. I'll talk about that in a bit later too. If I can get assignment 3 out today, then you'll get it in your sheet, but if not, you'll have to come to my office. But I'll send an email to let everyone know. Yeah. Does anyone have any other housekeeping questions? No? Okay. All right, let's move this away, and we'll talk about that shortly. This one. Okay, we've got a little bit of the notes left to finish. Can you tell them to stop giggling? Yeah, that's you. Okay. All right, we've got a little bit of the notes left to do today, and hopefully we'll finish it pretty early, and then I can talk about the exam for a bit, and then Wednesday we'll just do revision questions, okay? All right, so we looked at this on Wednesday last week. We've been doing second order constant coefficient linear ODEs. So that are ones like this here. And all I've done, we're doing exactly the same sort of thing, but now I've replaced these coefficients with things that you can say about an electric circuit, okay? So the capacitance, the resistance, and the inductance, and here's like the battery, okay? And often the battery is an alternating current, and so then you get something like a cosine or a sine here. We already ran through these, so I'm not going to go through them again. Suffice to say that the different types of solutions, remember, it depends on that what type of lambda values you get, if they're real and different, or if they're the same, or if they're complex. And then you get underdamped or critically damped or overdamped solutions, okay? So we're going to whiz straight into an example because we already looked at these. Now, this example here, how it doesn't give you the equation, I would not ask a question like this in the exam. If it was a question like this in the exam, I would give you the equation, okay? You don't have to remember where does the L go and where does the R go and where does the C go. I will give you the equation, all right? You don't have to remember anything silly like that. So we're going to jump straight into this example here. We've got an electric circuit and we are going to find the solution. That kind of looks really slopey, doesn't it? Which way is it sloping? Okay. I don't know if that's any better. Alright, so in the notes it says what? It says you can construct the equation something like this, okay? So if it was an exam question or assignment question, I would give you the equation. You don't have to figure that out by yourself. All right, so if we substitute our little inductance, resistance and capacitance value into here, what do we get? We get Q double prime. Remember, Q is the charge on the capacitor in the electric circuit. The resistance is 2. And the capacitance is 0.1, and that's like 1/10, and 1 over that will be 10. Okay, so that's the left-hand side of our equation. On the right-hand side, you want to put the battery, the little driving force. It's going to be 150 cos 4t. Okay? It's a bit wonky, isn't it? Okay, so this is a second order. It's linear because none of the Q's are timesing by each other. It's constant coefficient because there's constants in the front of the Q terms. And it's non-homogeneous, so we've got the right-hand side here, okay? When you're solving an equation like this, think about what we have to do. We have to look at the corresponding homogeneous equation. That's going to let us find the complementary function, the YC thing. Well, this time it's going to be a QC. And then you've got to look at the right-hand side to help you have a good guess at what the particular solution is going to be. Okay, so that's what we're going to do. Corresponding homogeneous equation is the same thing, but on the right-hand side, we're going to have 0. That's what makes it homogeneous. All right, we've got a characteristic equation. The second derivative will give you the lambda squared. The first derivative gives you the lambda. And the function itself, where there's no derivatives, is what gives you the lambda to the power of 0 term. Okay, so now we're looking for the values of lambda that satisfy this equation. Can we factorise it? No. Can't factorise this one, so we're going to use the quadratic formula. You guys have all got the giggles today. Minus b plus minus b squared take away 4ac. Okay, minus 2 on 2, that gives us minus 1, plus or minus 4 minus 30, that's 36. That's minus 36. Minus 36. Square root of that is going to be 6i. Divided by 2, that's going to be 3. 3i. Okay, so remember the alpha is going to be this real part here, and the beta is going to be this part here, the part that's in front of the I. And you don't have to worry about the plus or minus, and you don't have to worry about the I. You're just interested in that number that's there. All right, our function then, our complementary function, Q, because it's the charge of the capacitor. It's a function of time, because we're looking how the charge varies with time. And then we can just read the solution straight off of the formula sheet, right? So we have e to the alpha t times by c1, so that's our first constant of integration, cos of that beta t plus c2 sine of the beta t. Alright, I'll tell you something that lots of people do that's kind of really annoying, but it's just a silly little mistake. You're used to writing things as a function of x, right? So people will write qc as a function of t is e to the minus t, c1 cos 3x plus c2 sine 3x. Make sure you pick which variable you're using. Here we're using a function of time because of this one here. Okay, so don't mix up your x's and t's. Figure out what variables you're using and stick with it. Okay, that's our complementary function. That's half of our solution. We need the other half, which is going to be the particular solution. And this is the one where we're using the method of having a good guess, right? So you look at the right-hand side. Actually, let's do that first. The right-hand side is like cos 4t. You've got to pick the functional part of that right-hand side. The 150 is just a constant out the front. The 4 matters though, because you can't change this 4 into another number very easily. Q, oh gosh, Q is equal to, now if you have look up in your table of good guesses, it'll say if you've got a cos or a sine, your guess should have both of those things in it, right? So I'm going to guess A cos 4t plus B sine 4t. That's going to be my guess. And now all we have to do is try and figure out what the A and the B are. You can figure out what the A and the B are because this thing here has got to be a solution of the original equation, this one. Okay, so we're going to substitute it into here. We want to differentiate it once, differentiate it twice. So we've got all our bits and pieces ready. Oops. Okay, first derivative. Oops, minus. Okay. So we've got our guess, we've got our first derivative, and we've got our second derivative. By the way, before we go any further, you know how sometimes you make a good guess and it turns out to be a bad guess? Do you reckon this one's going to be good or bad? Good or bad? What do you reckon? Good. Why good? There's no e to the something. Yep. So what you want to do is you want to look at your guess and see if you can match anything in here. So this is going to be a good guess, I can tell, for two reasons. One, like Jonathan said, there's no exponential down here. Okay. The other reason it's going to be a good guess is because here we're worrying about 4 t's, and here we've got 3 t's. Okay. So these things are quite different. So we know that it's going to work. All right, we're going to substitute these things. Remember, this is a second derivative. I've just used different notation, which is a bit bad. Here's a second derivative too. So we're going to stick these into here. Bless you. Equals. Okay, second derivative. Okay, what have we got? Plus 2 of the first derivatives. Plus 10 of the guesses. Equals the right-hand side, 150. Okay, so now we've got one equation, this part here, right? There are two things that we don't know. We don't know the A and we don't know the B. One equation, two things we don't know. But the good thing is we can split this into its linearly independent parts, okay? Okay, what are the linearly independent parts? Poor Alex told me there was no lollies last Wednesday and he's got his hand up like a shot. Yes? Sine and cosine, that's right. Why do you sit up the back and ask me that? All right, ready? Watch out. Oh, that's not too bad. Okay, sine and cosine. Okay, so collect together the cosine 4t's on each side. Oops, this one. $150. And the sine ones. Okay, so let's just tidy them up a little bit. So you've got minus 16, that gives me minus 6a, 150. This one gives me equals 0. Who's getting messages? Sounds like a WhatsApp. Okay. Alright, so now we've got two little equations which look much nicer. Lucky. Two little equations which look much nicer and we've got to solve them for A and for B. If you really love linear algebra, you can stick them in as a matrix equation. If you don't love linear algebra, we can just rearrange this one and substitute it into there. That's what I'm going to do. That gives you a hint about whether I really love linear algebra, doesn't it? Okay. B is equal to minus, and I'm going to divide it by 2, 4 over 3a. That's the second one, and then I'm going to substitute that into the first one. Oops, minus. Minus 18, minus 32, that's 50, right? Okay, divide both sides by 50 and then multiply, oh gosh, got off the page. Divide both sides by 50 and then multiply by 3. Bless you. Alright, so we were able to manage to find good values for A and for B. Remember, if you make a bad guess, or if you make a good guess that turns out to be bad, but you didn't notice, what will happen is you won't be able to solve these equations nicely for A and B. Okay, so why did we care about that? We've got B and we've got A. We cared because now we can write down this particular solution, okay? So it's equal to A. There we go. Okay, so we've got a complementary function and we've got a particular solution, and as soon as you've got both of those things, you can write down the general solution. Is that better? Oops. Oh gosh. There we go. Okay, that's the general solution for this equation. This question's still got some questions left to... This question's still got some questions. We've still got some questions left to answer in this one. Does anyone have any questions, though, before we talk about them?
When we made the good choice there, if that doesn't work, we just times that by the t outside, so it'll be t sine 4t.
It'll be t sine... It'll be t times by this thing here.
Yeah.
It'll be t times by a cos 4t and t times by that one as well. Actually, the next example we do's got that, so you'll see it. Okay. All right, the first thing we have to do... That looks wonky today. First thing we have to do is use those initial conditions, and that's going to help us find those two constants of integration, right? Constants of integration are C1 and C2. Okay, cos of 0 is 1, so this one is 1. Sine of 0 is 0. Minus 9, cos of 0 is 1. And sine of 0 is 0. Oops, 0 equals 0. Okay. That's the first constant of integration. The next one is you can use the condition on the derivative. Remember, when you use the one on the derivative, you have to find the derivative before you're allowed to substitute the t is equal to 0. Okay? You have to find the derivative of this thing here. Be careful, because here's a product of two functions. You've got to use the product rule here. I'm going to put 9 in for C1 now. So this one's going to be 9 times 3 is 27. Looks really nasty, but once you put t is equal to 0, as we know, it's much better. We go. All right, so we've got C1 and C2 and we can put it all together. Oops, sorry. Ah. Okay. go. All right, that's still a solution to this problem that corresponds to those initial values. Does anybody want to ask any questions about that one? We've still got a little bit of work to do. Okay, has everyone got those ones down? There's a couple of little extra questions at the bottom of this one. So we've done this, we've found the solution, we've used the initial conditions. Now here, is the system critically damped? Oops, one more wonky. Is the system critically damped, overdamped or underdamped? That's the question. Look in your notes, what do you reckon? Critically damped, overdamped or underdamped? Hey guys, push up, thank you. So critically damped, overdamped or underdamped? No one wants lollies today. Underdamped. The damped values are complex, that means it's underdamped. Okay. All right, there's another question. What happens after a long time? That's the other question. What happens after a long time? Think hard. Look at that solution and think about what happens when t gets large. What approaches 0? The whole thing? Yeah, just the first bit, right? If you make t very large, that e to the minus t is going to get super small. And so that first part there is going to disappear. And then all you're going to have left is the last part. All right, I'll tell you something interesting about that. When we used the initial conditions, what did that help us to find? Yeah, C1 and C2. So that found us the 9 and the 13, right? Minus 13. So the initial conditions appear, well, they don't appear, but they help you find something to do with that first part, right? After a long period of time, you don't have any of that stuff left. You've only got this part at the end. So the moral of the story is here, after a long period of time, it doesn't matter what the initial conditions were, the whole system is going to settle down to what it wants to do anyway. Okay? So this goes for electric circuits, it goes for any oscillatory thing like this. Okay. There we go. All right, so that's what happens after a long time. All right, does anybody want to ask any questions about that one? Yeah, Michael.
Why did it say that Q equals infinity, but then you just like T is like
Yeah, okay, because when you have the cosine of a large number, it doesn't settle down to one value, it still oscillates. So it doesn't matter how large it's going to be, you still can't tell. So you can put, this kind of means Q as t gets large, and it's still going to be oscillatory, but it has nothing to do with the initial conditions that only come in there. Yeah? Does anyone have any other questions? No? Okay. Everyone done with that one? Hey guys, I'm not going to talk over you. You guys and you And everyone else on this side being quiet because they know I'm coming around. All right. The next thing we have to talk about is, if you have a look at this solution that we've got here, by the time you are a long time after you've started the circuit, all you've got left is this one, okay? All you've got left is this one, and you've still got this same battery going on, this same applied alternating current going here. So you've got an applied driving force that goes like a cos 4t, and you've got a solution here that goes like a cos and a sine 4t. And I'll tell you what's really useful. It's really useful if you can look at this long time solution and compare it more directly with what's going on in the applied force, okay? So that's what we're going to talk about now. So wouldn't it be nice if we could just write it as a single cosine, and then we'll be able to compare them. Okay. All right, so these are the things that we already know. The solution to the last example looks like this. It's two separate components. The first one is called the transient solution. It's called the transient solution because it doesn't stay for very long. The second part of the solution is called the steady state periodic solution. Steady state because that's what it settles down to, and periodic because it's still periodic. Okay? All right, we already talked about this. The two arbitrary constants from the initial conditions disappear after a while. Okay. All right, this is the question that I just asked. The steady state, what does it look like and how does it compare to the driving force? That would be really useful. Okay? What you want to do is you want to rewrite it. All right, now these notes are, here we go. No, that's okay. All right, what you want to do is you want to write it like one of these two things. One of these two things so that you can compare it. And the example that we've just done, we'd want to write it like this so that we've got a cosine because that's the driving force, and we'd want this thing to be a 4. And then we could compare it with this driving force with this frequency, and then there'd be this phi phase shift. Okay? And that's what we're looking for. Okay. So this is how you do it. I'm going to whiz through this because you kind of need to know how it happened. But it's okay. All right. This is the solution that we guessed, remember, except I think we had our A's and our B's switched over. Let's say that we wanted to write it as one sine function. We actually want to write it as one cosine function. But for example, let's say you wanted to write it as a sine function with the same driving force frequency and a phase shift. Now you can go and look up your formula sheet for your trig formulas, and you can change this sine thing here into one that looks like this. Okay, and now this thing looks like a sine omega t. I'm going to match this sine omega t with that one. And then this little a has got to be equal to big A times cos phi. So that's that one there. And then I'll have this part here, and the cos omega t is going to match this cos omega t, and this b is going to match the a sine phi. Okay, so there are two things we want to find when we do this. We want to know what the a is, and we want to know what the phi is. And now we've got two little equations that are going to tell us what the a and the phi are. Okay? Now, if you're clever, you can see that if I square this one and add them together, I can use another trig formula to get this thing out. So now I can find my a. Don't forget, we already found the little a and the little b. And you can also do some other fancy rearranging and find out what phi is. Okay? And you can do it one of two ways, and that's fine. Okay. So once you know how to find the big A and you know how to find the phi, you can write it like this. How can you write it? You can write it like this because now we know the phi and the A. And if you do a similar kind of argument but put a cosine here, you can get something to find the phi and the A, and then you can write it like this as well. Okay? So that's what we would want to do for the last example. And here it is. We're not actually going to do it. I've done it for us. You guys, shush up. All right. In the last example, we've got 12 and minus 9 for our little a and our little b. So you can find the big A and you can find the phi, and then you can stick it in like that. And the solution then looks nastier, but you can actually compare it very nicely to the driving force. The driving force, remember, was a cos 4t. So you can say that this is going at the same frequency, but there's a little bit of a lag, which kind of makes sense because if you think about it really simply, as the electrons are going around, which they're not really, they're only moving a little bit, but as they're going around, there's a little bit of a lag from when they get on the capacitor from when they were charged up and forced by the battery. Okay? But that tells you a lot more about the system than it does by writing it in the form that we wrote it. All right, one more thing to talk about. It's 1:45. All right, let's do it now. Okay, so we're going to do this example. It's nearly the same, but this is going to show us something extra that we didn't get last time. Oops, don't need that one. Okay, so once again, don't forget, I wouldn't give you a question worded like this in the exam. I'm going to tell you what the equation is, okay? Okay. All right, we can write down the equation then. L is equal to 1, R is equal to 0, so there's no first derivative term. C is equal to 0.01, so 1 over C is going to be 100. 200 sine 10t. Okay, same thing again. We're going to look at the corresponding homogeneous equation, and that's going to give us, what's it going to give us? The complementary function. Okay, so here's a homogeneous equation, and you solve that one by writing down the characteristic equation. Okay, now this is what I harped on for ages about every time. When you've got one of the terms missing here, be very careful about what you write down here. Okay, lots of people, it's really easy to make the mistake to say 100 lambda, because you can see a Q and you want to put a lambda. But the lambda term comes from the first derivative, right? And there's no first derivative. So when there's a term missing, just be extra careful about which one's missing from here. Okay. Lambda is plus or minus 10i. So these are complex lambdas again. Alpha this time is going to be 0. And beta is 10. So we don't have the exponential term out the front. There's our solution. What's that, our solution? That's our complementary function. That's going to be part of our solution. Okay, so the next thing to find is the particular solution. Okay, so now we're going to say, let's do the method of having a good guess, and we're going to try this thing here. All right, now this is going to be a bad thing to try, right? Because if I try this one, or if you have a look, this thing here is exactly the same as this thing here. Okay, so if you want to add these two things together, by adding this one, you're not adding anything new. So if I tried to substitute this into the differential equation, I'm going to get bogus values for A and B. It's just not going to work. All right, so let's not do this one. Okay, so let's not try that one. Okay, so you don't have to do anything else fancy. All you have to do is multiply what you originally guessed by t, multiply everything through by t, and then have another look and make sure it's different. Okay, and if we compare this one here and this one here, we can say yes, they're different. They're linearly independent from each other. If you could still see that they were the same, multiply through by t again. Okay, does anyone want to ask any questions about that? If you have to do one of these in the exam, you don't have to show you're working. All you have to do is try this thing or say this thing, and then you can say, no, that's not going to work, and you can try something else straight away. Okay? You don't have to go through that whole process. Yeah. Even if there's one term the same, you've got to do it. If you're worried, just do the working, and you'll see if it's going to work. Then it's fine. If it doesn't, it's not.
But you have to multiply that one term,
No, you multiply the whole guess. The only time it's different is when you have something like, I think it's different. Actually, I'm not sure until I try it myself. If you had something like an exponential and a polynomial, and the exponential part was a problem, I think you might only have to multiply that by the t, not the polynomial part. But I would do that by hand myself just to check that that's the right thing to do. Yeah. Okay. What are we doing now? Okay, we're going to substitute this into the differential equation. So we want to find the first derivative and the second derivative. Be a little bit careful, because now we've got to use the product rule here and the product rule here. I'm going to go right over here because I know it's going to take up lots of space. Bless you. Okay, so that's the first part. All right, these two are going to join together, and I'll have minus 20 of these. And what else? Something else is going to join to those two. And I'll have plus 20 of those ones. Okay? But now what we have to do, I'm not going to write it out again because I'm too lazy. We have to substitute this into the differential equation, this one up here. Oh, I know, it's painful, isn't it, Jason? All right. At least you don't have to do the first derivative. That's kind of good. Whoops, that's not. That's just the second derivative. Crikey. All right, plus 100 of what we're guessing. Okay. That's better. I'm going to go on to the next page already. Okay. So now we've got two things that we don't know. We've got A and we've got the B, and we've got one equation, but we can split it apart. All right. Equate coefficients of. All right, what are our linearly independent functions this time? What are we going to have? This time we're going to have 4. Yeah, we're going to have sine 10t. That's this one. We're going to have t times cos of 10t. T is not a constant, right? So that changes the function. We've got a cos of 10t and we've got a t sine 10t. Okay, we've got 4 of them. Bless you. Equals 200. Okay, so that's one done already, and from this we can see that A is minus 10. Okay, so far so good. The next one is t cos 10t minus 100A. This one, plus 100A, and there's 0 of those. Okay, so this equation doesn't tell us anything new. We already know what A is, but this is satisfied whatever the value of A is. Okay, so even though we don't get anything new, we want to make sure that this equation here isn't going to be violated, I guess, by this one. Okay, so you have to make sure these things are consistent, and this is fine. So even though it doesn't tell us anything new, you have to make sure that still things are okay. All right, what's the next one? So we've got 20b is equal to 0. Okay, that gives us our b value. And the last one is, oh no, we did that one, sine. This one. Okay, same thing with this one. It doesn't tell us anything new, but at least it's not contradicting stuff that we already know. Okay, so sometimes you get more equations than what you're trying to find. This time we've got 4 equations. We're only trying to find 2 things, but as long as they're all consistent, that's fine. Okay, why did we care about these, A and B? Because I told you that we did. Here we go. They come up in this one here. So this is going to be our particular solution. Okay. All right, so we're not finished, but does anyone want to ask anything so far? No? Oh, sorry. Looking straight past you. Michael, yeah.
If the first try you say doesn't work, you just say it doesn't work, and you try the second try, but the first try did work, would you see it?
That's a good question. I don't know. We can test it. I can test it in the break if you like. Yep. Okay, we'll test that out. Does anyone have any other questions? Not yet. All right, I've got a question for you. We've still got a bit to go in this example. We've got to find out the C1 and the C2, and then we have to talk about something that we're going to notice. Do you want to do that now, or do you want to do it after the break? Who wants to do it now? Who wants to do it after the break? Who wants to do it now? Who wants to do it after the break? All right, now wins. Okay, we'll finish it now. We'll still have 10 minutes, I promise. And then we'll have a break. Okay, so this is our general solution. You're putting up 2 hands now. I think you still would have lost. Okay. We're going to use the initial conditions to find C1 and C2. What have we got? Q of 0 equals 0. Okay, that's nice and easy. Yeah, but we got a 0 in here. Yep, so that's nice. Okay, then you want to use the first derivative. Remember, you've got to find the first derivative first. Oh, C1's 0, so let's not even bother. All right, so 10 C2 close. Okay, be careful when you get to this last term, because you've got to use the product rule. Okay, you've got t times by cos of t. So make sure you use the product rule. Plus okay, 10 C2 okay. Okay, why did we care about C1 and C2? We cared about them because now we can stick them into here. C1 is 0, C2 is 1. Okay, that's our solution. Don't get excited yet. We're going to write some more things about this one as well. As soon as everyone's done. Okay, so last time we asked the question, what happens when time gets large? We're going to ask the same question here. What happens when time gets large here? Yeah, it becomes the cosine one. What else about it? Yeah, it's getting bigger and bigger, okay? This one's just going to oscillate between 1 and -1. This one's going to this part here goes between 1 and -1, and this one grows and grows and grows. So this part gets bigger and bigger and bigger, okay? Let's write some of this down. As t approaches infinity, gets bigger in amplitude. Okay, gets bigger in amplitude. So the solution that we've got is oscillatory, and the solution is getting bigger and bigger. That means the oscillations are getting bigger and bigger, right? Okay, there's another course where they talk about this problem, and the guy that used to teach it used to bring in an electrical circuit, and he used to make it up so that it was like this, and he used to put it on the desk, and then he used to turn it on, and what do you think would happen? Yeah, it'd explode. Explode. Don't do this. This is called resonance, okay? If you go out and you build electric circuits and you're an electrical engineer, don't build circuits like this. If you're a civil engineer, don't build buildings and bridges like this. If you're a mechanical engineer, what are you going to build? I don't know. But don't build things like this, all right? I'm not driving over any of your bridges. Okay. Okay, all right. Does anybody want to ask any questions about that one? No? So I think I've said, let me just check. Did I say everything I wanted to say? Okay, oh, that's what I wanted to say. Okay, the reason that this happens, this stuff here, the part that comes in here and here, that 10T here is coming from this part here, right? What happens here is this is the natural frequency. This part here will determine the natural frequency of the system, and this part here is the driving force, right? And what happens here is the natural frequency here is 10, and the driving force is 10. So if the natural frequency of the system matches the driving force, that's when things start to go a little bit crazy, and that's when things will go bad. You remember we looked at the Tacoma Narrows video, which somebody else already showed you. That's what they reckoned, they originally thought happened there, okay? This kind of thing was happening. The wind was at the natural frequency of the bridge, and then the oscillations got large and it fell down. All right, I think that's all I wanted to say. Okay, let's have a break for 10 minutes, and after the break I'll talk about the exam. This one. Don't forget, if you've got questions you want me to do on Wednesday, bring them down and put them in my box, or send them by email by today. That'll be too late after that. We'll come back at what time? 20 past.
to ask you something.
Okay. All right, let's have a quick talk about the exam. 20 marks, that's right. Pardon? You need 40% though, right? Yeah. So long as you've still got enough assignment work to pass the course. Yeah. All right, listen up. This is the front cover of the exam. You're supposed to read it carefully and follow the instructions, but I understand that when you're in the exam room it's hard to read carefully and follow instructions. So read them now and remember the instructions. Don't stress. Stress doesn't help you. It's not your friend. Take a deep breath and try and relax. You can't bring any calculators. Okay? There are no questions in this exam. I can put this on the web page if you like. There are no questions in this exam for which you will be helped by a calculator. I'm very careful to choose all these questions so that things work out nicely. If you are getting a question and it turns out to be 47/13 plus 2 halves, that's one. 47/13 plus 4/5 maybe, probably you've made a mistake, all right? I'm not that mean in the exam and I haven't given you calculators. They're going to be, if there are fractions, they're going to be easy peasy ones. A half plus 3 halves, okay? Maybe a third plus a half. Hopefully we can all manage those. Okay. There are 6 questions in this exam, the same as the ones that are online. You should answer all the questions. Here's one in bold because nobody ever follows this instruction. Begin each question on a new page, okay? I'm telling you that because when we mark the exam, what you do is you go through the pile and you mark all question 1s and then you mark all question 2s. If it's hard for me to find question 1 because it started halfway down the page after question 4, that's not very helpful for me, and you don't want somebody marking your work who feels like they're not very happy. Okay. Pardon? Yeah. Yes. Okay, I can talk about that in a minute. Okay, begin each question on a new page. If you run out of space in your exam book, you're going to get a 16-pager. If you do run out of space, most people don't, but if you do, make sure you put your name on the extra book. Every year there's 1 or 2 second books that don't have their name on. That's tricky as well. Okay, you should show all your marking by hand, all your working by hand, which you kind of have to do when you've got no calculator anyway. You can use the results of earlier parts of the question when attempting the latter parts, even if you haven't completed the earlier parts. I can't remember if there's any questions that this is of relevance to in this year's one or not, but sometimes I'll say, do this integral, and now you can use this integral here, okay? If I've given you the result of that integral, you can just use it even if you can't do that first little part, okay? Leave your answer in terms of square roots, log, and stuff in its simplest form. If you've got log of 1, I expect you to know that that's equal to 0. If you've got log of 4, it's log of 4, okay? If you've got sine of 5, then that's what it is. If you've got sine of pi on 3, I expect you to know what that is and write it down, okay? You may detach the formula sheet. So what happens is you have your exam, right? That's the front cover there. And on the inside, obviously, are the questions. The very last page is the 2-sided formula sheet. If you want to, you can rip that off if it's easier to use like that. But just make sure you stick it all back together when you hand it up. Okay. Other questions to talk about? If you are doing a question and you made a mistake, don't rub it out if it's in pencil. Just put a line through it and do it on the next page. Okay? Same with pen. Don't scratch it all out. Just put a line through it and do it on the next page. If what you had to start with was correct, I will mark that one. You might lose a mark for deciding it was wrong, but you will get most of the marks that you got in that section as well. Okay? Don't rub it out. Don't rip it out. Don't completely scratch it out. Just put a line through it. Okay, what else? I've put 3 past exams on the website. This exam to me looks very similar to those past 3. The first question is about, what's it about? Matrix equations, solving systems of linear equations. The second question is about the same kind of thing but with a parameter in it. The third question is eigenvalues and eigenvectors. The fourth question is something to do with, actually the fourth and fifth questions are something to do with techniques of integration and ODEs, including this stuff, but not so much the electrical circuit stuff, but second order ODEs. The last question is applications of integration, so area, volume, centre of mass, moment of inertia. Okay, the structure is exactly the same. Here are the marks for each question, so you can see how much is on linear algebra and how much is on calculus. All right. Does anybody want to ask any questions so far? 27 for that one, yeah. Normally that's a big one because there's just all the different techniques. It's broken up though inside. Does anyone have any other questions about this stuff? Yeah? Yeah, you should have like a scribble sheet as well. Yep. Okay. Okay, I've got some more things to say about the exam. The whole exam has got 90 marks in it, okay? And I do that for a reason. You've got a 3-hour exam that's 180 minutes. That means you've got 2 minutes per mark. That means if a question is worth 10 marks, you should spend 20 minutes on it, or less, or maybe 1 minute more, but not half an hour and not 40 minutes, okay? So budget your time wisely, and it's easy to do it because it's 2 minutes per mark, okay? There are 6 questions, we already talked about that. 37 of them are for linear algebra and 53 for calculus, because we spend more time on calculus than linear algebra. It's not what you wanted to hear, is it? Okay. Do all the questions, start each question on a new page. The formula sheet is already provided. It's the same as the one on the website. Don't bring any calculators, show all your working. Okay. Does anybody want to ask anything more about that? I've got more things to say though. Yep, Alex. The formula sheet on the website is exactly the one on the exam, that's right. Does anyone have any other questions? No? Okay. Yeah. It's the same kind of stuff as what we do in the examples in class. You know, when we do an example in class, sometimes the very first one we do, we'll do extra kind of working, but from after that, we'll just do it. What we do in class normally, not necessarily the very first one, is fine. That's the kind of amount of working you should show, so that I can see how you got from one to the next one. Yeah.
Like, so say if we've got a product rule derivative or something, we
Yeah.
have to show each, so, you know, oh,
You know how we did the product rule today when we were differentiating something to substitute it in? Yeah, that's fine. Yep. But I wouldn't want you to go from the initial to some very shortened, factorised form of the derivative. Yep. But no, you don't have to do all that stuff. What we did in class is exactly what you should do. Does anyone have any other questions? No? Okay. Next page. A couple of people have asked me about what they should do for revision, and this is my advice. Do as many questions as you can. Now, the important word in that sentence is not many, but do. Do as many as you can. Don't sit down and watch the lecture recordings and don't do them yourself. That doesn't help. There's a professor at Sydney Uni. She was the first professor at Sydney Uni, actually. First female professor at Sydney Uni. And this is what she says. You can't learn to play the piano by reading a book or watching a film about it. But everyone expects to do that with mathematics. You can't. It's the same. You actually have to do it. All right? You have a question, and there is a whole thought process that goes on between looking at the question and writing the first line of your working down. That is the part that you need to practice, okay? Do that part. Don't look at the question and straight away look at the answers and go, oh yeah, that's what I have to do. That thought process is important. You can't just do that in the exam. Don't do it when you're revising. Do as many questions as you can. All right. Try one past exam. Don't just do all the past exams and that's all you do. Do a past exam, and that will help you to figure out where there are things that you can't remember. Then go back and do some of the examples that you've got. So you've got examples from lectures, you've got tutes, you've got homeworks, which aren't even up there. You've got assignment questions, and you've got the textbook, okay? Go through the whole course, not just the parts that you had trouble with, the whole course, but concentrate on the parts that you have trouble with. Then try another exam, time yourself, don't look at anything else, see how you go. find the gaps that are left over, then do some more questions of the whole course, concentrating on those gaps, and then do another exam again, okay? Just keep doing that. Don't just do the past exams, that's not going to be enough. Okay. When you are doing these past exams, use the formula sheet that you've got, and if there's anything that you actually need to look up, make a note of it, because that's something that you need to remember, you need to know and understand. All right. Does anybody want to ask any questions about that? That revision? No? Okay. Here's my advice for in the exam. Don't panic. I already said don't stress. Don't panic either. When you've got your reading time, you've got 10 minutes reading time, read through the questions, decide which one you're going to do first. You don't have to do question 1 first. My advice is to do the one that you think is the easiest first. If you do the one that you think is the easiest first, probably you're going to go faster. That means you'll have some time up your sleeve. And you'll build your confidence up, and then that panic and stress will start to go, okay? Start with the easiest one, then the next easiest, then the next easiest. Start each one on a new page, make sure they're numbered nicely. Okay. Manage your time. You know that you've got 2 minutes for each mark that's there. If a question is worth 5 marks, that means you should spend 10 minutes on it. If you spend 10 or less, that's fine. If it gets to 10 and you've only got a tiny bit to go, just finish it off. If it gets to 10 and you still can't figure out how to start it, don't waste any more time on it. Go on to the next one, okay? All right. If you finish early, check your answers. So most of the time in class, if there's a way to check your answer, I have either checked it or told you about it. If you find the inverse of a matrix, get your inverse, multiply it by what you started with, and make sure you get the identity. If you're solving a differential equation, substitute your solution into the equation. Everything should work. If you're integrating something, integrate it. Differentiate it. See if you get what you started with before you integrate it. Okay? There are lots of ways to check your answer other than just reading what you've written down and show you're working. Okay. Does anyone want to ask any questions about that stuff? No? Okay. All right, consultation times. I'll put these on the website. During the swap vac week, I'm not going to be here on the Monday or Tuesday, but I'll be here on Wednesday and Thursday and Friday. Wednesday and Friday in the morning and Thursday in the afternoon, okay? The week of the exam, I'll be here on Monday in the morning only. So don't come in the afternoon because I won't be here. If you want to come at a different time, you can email me and we'll sort something out, bless you. Or you can come by and knock on my door, and if I'm free, then I'll talk to you then as well. But don't count on that unless you've emailed me first. All right, there are going to be past sessions, but I'm not sure on the time yet. I'll post that on the website and email it out. And the Maths Help Centre will be open as well. Oh, that's the other important thing. If you come and see me, or if you come and see the Help Centre, if you come and see one of the past people and you want some help, don't just come and say, oh my gosh, I can't do integration. Come and show me what you've been trying to do, because that will help me understand the bits that you can't do, and it will help me give much better explanations. So bring me the stuff that you've been trying, okay? What else? Oh, some of you have done this already, which is great, but most of you haven't. Please make sure you fill in the course evaluation thingos. These are the things that I have to say about this. Make sure you write the things about the course in the course evaluations, and the things about teaching in the teaching evaluations. Sorry, I'm going to sneeze. Things about teaching in the teaching evaluations. This year there's been a heap of changes to this course, so if you have any constructive feedback, I would love to hear it. These are the things that I'm interested in. I'm interested in the assessment structure. Okay, the quizzes are new. Were they helpful? I'm interested in what you think about the MATLAB and Excel, and I know that's the part about this course that probably most of you don't like, but I'm interested to hear what you like and don't like about it. Constructive, okay? The tutorial structure and timing, are the whiteboards helpful and the group work helpful, and are the tutes long enough? That's what I'm really interested in. Are they long enough? Because MME1 has got hour and a half, we've only got an hour, so I'm interested in that one too. And what else was helpful and what else wasn't helpful? And when you come to do the teaching evaluations, all you have to say is how fabulous I am. That will be fine. Okay. That's it. Does anyone have any other questions? No? Pardon? Yeah, lecture on Wednesday. We'll do revision. Make sure you send me questions. I've got some, but not very many. I'll see you on Wednesday.